Okay, good morning. So we're going to continue today with our discussion of molecular shapes, and then we'll move into polarity, molecular polarity, and then we'll look at two different models of chemical bonding. One's called hybridization, and the second one is called molecular orbital theory. Okay, so let's remind ourselves a little bit about the molecular shape. The idea is that you have a central atom and some number of surrounding atoms. And we use the notation AB, where A is the central atom and B is the surrounding atoms. Now you may also see, I'll just write it next here. You may see an X for the surrounding atom. So they'll write it like this. And it turns out that geometrically what we observe is that there are essentially 5 basic arrangements. And those 5 are where you have 2 surrounding atoms, 3, 4, 5, and 6. And we give names to them. I'm going to kind of draw a little picture of them first. So the A is in the center, and then the B's are surrounding. So something like this. And that one's called linear. And it's linear, it's a straight line. And so we tend to also give an angle, theta, for this. And so the angle is based on, drawing a line from the central atom to one of the surrounding atoms, and then just rotating an angle through to the next surrounding atom, the second one, the closest one you come up to. And so for linear, that turns out to be 180 degrees. Okay, so what we find then is that if you have one central atom and 2 surrounding atoms, you have this linear arrangement. So that's seen in all kinds of, carbon dioxide, for example, CO2 does that. And then if you have 3 surrounding atoms, now the central atom is here, and you have 3 surrounding atoms like that. Look at this little triangle. And this one's called Trigonal Planar. And that's 120 degrees. Okay, so an example of that is a molecule called borane, BH3. You have boron in the center. Actually, I can write a couple of examples here. CO2, BH3, right? 3 surrounding atoms, 1 central atom. The fourth one, or the third one, is you got the central atom here, and now it becomes 3-dimensional. So it looks like a little, to me, it looks like a little pyramid. They call it a tetrahedron. So it's called tetrahedral. And that 120 is from here to here, right? That's the angle going from one to the next one. All of those angles are 120. But this angle ends up being a little bit less than that. It's 109.5. And the famous example of this is methane, CH4. Okay. Then you get to a couple that are a little bit more, exotic. You have a central atom and you got 5. So what happens when you have 5 surrounding atoms is you end up with like the little trigonal planar in the middle. So in the middle, you got a trigonal planar, right? That's like the little triangle. We're just sort of drawing it. Sometimes it's referred to as equatorial positions. But then you got a second angle. You're going from here to here. So that's 90 degrees right there. And then this one's 120. So it's, in a sense, it's sort of like a linear. You have a straight line between the central atom and the 2 surrounding here. So that's linear. And then you have a trigonal planar in the middle. But this one's called trigonal by pyramid. And again, there's 2 angles. There's 120 and 90. And, phosphorus does this sometimes as a central atom. So PCl5, phosphorus pentachloride, is sort of the famous example of this one. Okay. And then the last one is AB6 or AX6. So now you got a central atom. And this one is kind of like you're combining 3 linears. Okay, and all the angles are the same. It's octahedral. And this is all the angles are 90. SF6 sulfur hexafluoride is the example of that. So I have a couple of these here just to remind you. You got these ones here. That one there. That one there. And we have a linear too. All right, so we'll start with this. You got your linear right here. AB2, straight line 180 degrees going from here to here. Okay, there's your linear. Trigonal planar looks something like this, right? So central atom, 3 surrounding atoms, 120, right? And if you think, again, you think about it, 120, 240, 360, do a whole circle, that's 360, right? So BH3. Tetrahedron or tetrahedral. So that's one right here. Got the central atom, 4 surrounding atoms. And again, you know, see how it's like 3-dimensional, right? It's no longer so easy to draw. So there you go. There's your tetrahedron, 109.5 degrees. And then, like I said, this trigonal bipyramid, it's almost like you have 2 structures in one. You have a linear in the middle here, but then you also have this little triangle, trigonal planar, around the center, axial positions, equatorial positions, kind of like a globe. Okay, so you get 2 angles. You have a 90 degrees here, and then you have 120 going from here, just like the trigonal planar, PCL5. And then the last one, like I said, it's like 3 linears, straight line, straight line, straight line. So in a way, it's kind of analogous to p orbitals, right? You have a px, a py, and a pz, and they're, you know, 90 degrees or perpendicular. Same kind of thing here. So sulfur hexafluoride, which is kind of a famous compound. One of the reasons it's famous is because of the structure, octahedral. Okay, so this one's octahedral. And there's your 5 basic shapes. Okay. Now, what you'd want to do is you want to be able to kind of go back and forth. So given the formula, you know, can you figure out what the shape is? And, you know, as long as it fits that formula, you're set. You can pretty much do that. But something happens when you start adding lone pairs to the central atom. The lone pairs to the central atom mess things up because they add an extra electron group. So they kind of act like one of these surrounding atoms, right? So we have ways of representing those lone pairs. We can represent it using these lobes here. So that would be like a lone pair, right? It's only on the central atom. So notice this one has 3 lone pairs and 2 surrounding atoms. So you would say, oh, it's AB2, except that these lone pairs take up positions as well. So, you know, you have to kind of take those into consideration as well. So there are, you know, there's another set. So let me save this one. So there's another set of these structures. And the first one is AB2. And it has either 1 lone pair or 2. And this one is bent. Let me draw a picture of it. Central atom bent. 104.5. Now it depends. This one right here is typically close to 120. And this one is close to 104.5. Okay. But it can be kind of in there, anywhere in that range. So the examples of this one would be, I'm going to write it here. SF2. I'm sorry, SO2. And then H2O. Those are the kind of famous ones right there. So this one's around 120, this is 104.5, but both called bent because they both kind of take on this arrangement right here. Central atom, 2 surrounding atoms, but they have lone pairs. I didn't draw the lone pairs in here. Okay, the lone pairs end up making a difference. So that's the first one. I want to show you why the lone pairs are important in terms of the bent. And I guess what I'll do is I'll show you with water first. Do this one here. Okay, so I can't use the red one. I gotta use the black one here. So water has two lone pairs, right? We know that from its Lewis structure. So there's our two lone pairs. Okay. And then it also has two hydrogens, right? So in a sense, this is a representation of water, H2O, although it looks kind of, oh, shoot, I'm sorry. I used the wrong. The black ones usually have 4 holes, but sometimes they, and I got one of these kits mixed in here that has 5 holes just to mess it up. Okay. So the water has 2 surrounding atoms, AB2 or AX2, but it also has 2 lone pairs. So there you go. So if you ignore the lone pairs, you know, you got a bent structure. That's bent right there. Okay. But see why it's bent. The reason it's bent is because of these 2 lone pairs. They're taking up space. So they're pushing these hydrogens closer to each other. Compare that to the linear. If you don't have any lone pairs like a linear, okay, there's nothing pushing against these hydrogens. So they're just, you know, moving away from each other as far as they can, so you get linear. But if you throw in a couple of lone pairs, they're going to cause it to be bent. They're going to push those hydrogen atoms with their bonds further away from each other, or closer to each other, actually. They push them closer to each other, and you get that 104.5. Okay. Now, what happens with the, I do kind of want to show this to you, the sulfur dioxide, SO2, that I just wrote there. I said that was 120. Okay. So let me see if I can get a good bond in here. Oh, again, I use that one. This one is like a little spy in there making things difficult. There's a lot of them actually. Okay. Interesting. All right, here we go. SO2. So there's the sulfur. The black one is the sulfur. The oxygen, 2 oxygens. There we go. So SO2, but it has a lone pair. There we go. So SO2, AB2, E1, right? E1 meaning it has 1 lone pair. Look how that lone pair, what it's doing, it's pushing these atoms down away closer to each other. They would be linear, they'd be a straight line, except the lone pair pushes them away. So if you actually look at it, that's going to be 120, right? If you think about it, 120, because it's kind of like a trigonal planar. But the name of a structure, we give the name based on the arrangement of the atoms, not the arrangement of the lone pairs. So AB2E1 would be 120. Your water, that angle's a little closer. It's 104.5. It's kind of hard to see because of the way these things are designed. But this one, the angle is smaller for water. So I put those, you know, angles in there underneath them just to show that. So AB2E1 would be bent. AB2E2 would be bent, but their angles would be different. And generally, you want to just memorize the angles. 104.5 for bent. 120 if it's, you know, AB2E1. And let me show you the next one. The next one is AB3E1. Usually there's no E2. If it's E2, it's a different arrangement. But this one's kind of funky. It's kind of cool. What you get is something that looks like this. Okay, it looks like a little pyramid. And this one is called Trigonal Pyramidal. Okay, and it's 107.5. I'm sorry, 107. I don't know where I get the 0.5. I'm just kind of making up numbers. 107. Okay, so let me show you that one. Okay, again, I have to show it to you with one where you got the right everything. Okay. Okay, so here we go. AB3E1, right? E1 means 1 lone pair on the central atom. So it looks like a little triangle, but it also looks puckered, we call it puckered. So it looks like a pyramid, right? So trigonal pyramidal. And there you go, 107.5. 107 degrees, very close to 109.5. This one doesn't change the angle all that much, but changes it some. Okay, so this one's not two-dimensional, it's three-dimensional. And if you compare this one to your trigonal planar, see the only difference, again, the only difference is this one has a lone pair, this one doesn't have a lone pair. And it makes a huge difference in terms of their shapes. That lone pair takes up space. And so that space results in a completely different structure. Okay. Next one, I guess to give you, I've got a few of them here, so I guess I could do this one. This one right here has 4 surrounding atoms. Well, let me see if I have any more that have 3 surrounding atoms. That one has 4 surrounding atoms. This one has 5 surrounding atoms. Oh, here's one. So this is an interesting one. AB3. And then 2 lone pairs. So not 1 lone pair like trigonal pyramidal, but 2 lone pairs, E2, right? The 2 means there's 2 lone pairs. So this one's funky. It's this, again, essentially it's your trigonal bipyramid where you have 5 attachment points, but 2 are lone pairs. So it ends up doing something like this. You've got the AB2 there, and then the third one is down here. It looks like a T. So the actual arrangement looks like that, and it's called T-shaped. 90 degrees, right? Okay. So if you get AB3, E2, you got your T-shape. Okay. So there's that one. Let's see, we got anything else? Let's have a, I think the next one you come up to, oh, here's an AB4. So this one is AB4. And so is this one. Both of these are AB4s. Both of these have 4 surrounding atoms, but one of them has 2 lone pairs. The other one only has 1 lone pair. So let's do the one with 1 lone pair. So AB4, E1. Okay, now you look at this again. We're going to look at the arrangement of atoms. You know, how do you name something? You got a straight line there, but then you got a bent there. So, you know, they call it a seesaw. I don't know. I guess the seesaw would be kind of like this, back and forth. I don't know. I'm not sure. They call it seesaw. So let me just try to draw it for you. Okay, it's sort of bent right there. And this one's a seesaw. And then it looks like you got a couple angles there, you know, but that looks like 90 actually. It's 90 degrees. All right, so from here to here is 90, from here to here is 90, from here to here is 90. But that's because you got 1 lone pair, you get this seesaw. Then you got one more that's got the AB4. It's got 2 lone pairs, so 2 lone pairs. So AB4E2. Okay, now this one's funny. It's cool. This is an important one historically because there's a anti-cancer compound called Cisplatin, where it has a platinum at the center, 2 chlorine atoms, and 2 ammonia molecules essentially attached to the platinum at the center. And so it takes on the same arrangement as this structure here. And the cis just means that the chlorines are on the same side. So you have 2 chlorines here, and then 2 ammonias right there. Yeah, that's called cis. Trans is where you have them opposite sides. So the 2 chlorines would be like one here and then one over here. So anyways, this one ends up being a square. And it's flat, right? It's flat because, again, those 4 surrounding atoms, which they sometimes call ligands, are attached to the central atom there in a square plane. So it's called square planar. 90 degrees. And then there's that one. And then do I have any others? I guess I got, you know, here's one. This is kind of funky too, because it's got 2 surrounding atoms. So it looks like it's going to be linear, and it actually is because it's got 3 lone pairs. The 3 lone pairs take up the middle. And so it ends up being linear. So this is AB2, E3. And so the arrangement of the atoms is a straight line. So this one's linear. So it's a second type of linear, and it's 180 degrees, right? There's your angles. It's kind of cool. So if you got 2 surrounding atoms and 3 lone pairs, you go back to linear. It goes back to that basic arrangement. And then the last one I was going to show you here is this one right here, which, oh, shoot. So this one has, oh, I see what happened. This thing came off. Okay. Interesting shape, right? You got central atom, 1, 2, 3, 4, 5 surrounding atoms. So AB5. And then 1 lone pair. Okay, now how do you draw this thing? You got a central atom here. And then you come up like this. Isn't that cool? All right, so, you know, it's a square, but it's also a little pyramid, so they call it square pyramidal. And it's all 90 degrees. Everything's 90 degrees, 90 to here, 90 to there, 90 to there, okay? So again, the arrangement of the atoms, the names of these are based on the arrangement of the atoms, not the lone pairs, but the lone pairs affect the arrangement of the atoms. So it's, they have an effect on it, but that's not part of the name, okay? So there you go. So you got 2 tables there. You know, it's a lot to remember. So, you know, you can print out these, you know, these tables and use those when you're doing problems. But the main thing is you got to be able to get the Lewis structure. If you can get the Lewis structure, you can do these problems because you can just match it up with these formulas here. Kind of cool. Let me see if I've got something here. I guess I don't. Okay. All right. So let me bring up a problem here. Okay. So what are the angles A and B in the actual molecule of which this is a Lewis structure? So here what they're doing is they're giving you the Lewis structure, so you don't have to draw the Lewis structure here. And I don't know why it says note for advanced students. Give the ideal angles. Oh, I see what they're saying. They're saying, look, if you really know what you're doing, you might like really put in the exact right angle. And so they're telling you here, look, just use the ideal angles, which are, you know, linears 90, trigonal planars 120, tetrahedrals 109.5, and then bent 109.5, trigonal pyramidal 109.5. So what their point is, you know, don't worry about whether it's 104.5 or 106.5 or 107, just put in the 109.5. So you're just counting the electron groups. So here they want you to do the angles. Look, there's 2 angles they want you to do here, A and B. Okay, so again, keep in mind the Lewis structure doesn't tell you the angles, but it gives you a clue, right? You know, we draw Lewis structures kind of like horizontal and vertical, 2-dimensional, and everything's 90 degrees. But we want to be able to get the actual angles from this VSEPR theory. So let's do A first. So what you do is you look at the central atom. A is going to be from a surrounding atom to another surrounding atom. That's what an angle is when we talk about this notation. So you identify that the central atom is carbon, and you go from H, you sweep out an angle to there. Now that looks like 180, right? So be careful. That's not 180. It's drawn as 180, but that's because that's a Lewis structure. So what you got to do is you got to say, okay, there's your central atom, C. So that's A. And then you got 3 surrounding atoms, right? 3 attachments, no lone pairs. So it's AB3. Well, what is the angle for AB3? It's a trigonal planar, so it's 120. So angle A is going to be 120. And the same is true for B. This is a trick question. They're showing you the Lewis structure, which is not the actual angles. since this is still the same central atom and you're going to the next surrounding atom, it's still going to be trigonal planar, it's still going to be 120. So the actual arrangement, here's your Lewis. I'm sorry, I already forgot what molecule it was. So it's H and then OH. Okay, this is acetic acid. Oh no, it's formic acid, right? That's formic acid. Okay, so there's that angle there, and then there's that angle there. Okay, well, it's AB3. So the carbon is at the center, and the three groups are like that, right? So you have your OH here, you have your H here, and you have your O there. I'm not showing the double bond. You can if you want to, but in terms of the arrangement, this is trigonal planar. So it's 120. All the angles are 120. We didn't say that for trigonal planar, one of them was 120 and the next one was 90 or anything. We said they were all 120. Okay. So for this one, then A would be 120 and B would be 120. So be careful with that. You can't, that Lewis structure will really mess you up if you just try to say, oh, I'm looking at it and there's our angle. You have to use the VSEPR theory. Okay, let me see if we have another one we can bring up. Awesome. Here's one. What are the angles A and B in the actual molecule that's the Lewis structure? So again, they give you the Lewis structure. This one happens to be methanol, which is wood alcohol. Wood alcohol is poisonous. What are the angles, right? Okay, so again, you got the carbon in the center. How many surrounding atoms are on the carbon? And be careful, when we say surrounding atoms, we really mean surrounding groups. How many atoms are physically attached or chemically attached to the carbon? The hydrogen all the way on the right is not attached to the carbon, but this oxygen next to it is. So there's one, this hydrogen is, there's two, this hydrogen is three, and then this hydrogen there. So you got 4 attachments, 4 surrounding atoms. That's AB4. AB4 is tetrahedral. Tetrahedral is 109.5 degrees. That's one of the basic angles, 109.5. So this is going to be 109.5. This is, well, actually, oh, shoot, what are they doing there? They're going from, oh, yeah. Oh, boy, that's a good one. That's really actually very good because it looks like you're going across 2 bonds, but you're really not. So let me show you that one. That's really good. I like that problem. Okay, so COH, HHH. Okay, so here's your angle A, and then here's your angle B. Okay, well, it's AB4, right? You got 1 central atom and then 4 surrounding atoms. And so you got tetrahedral, 109.5 degrees. So I'm going to kind of draw, I'm going to draw it this way. I'm going to draw the carbon in the center. I'm just going to pick one of the hydrogens and put it up here. Pick one of the hydrogens and put it down there. Pick one of the hydrogens and put it there. And then I'll do the OH over here. See how I just sort of draw the OH right there? Let me draw this a little more pretty. There you go. Okay, so there's your tetrahedron. So A to A was this angle right there. Okay, that's pretty clear. That looks like 109.5 degrees. But then they said go from here to here. So they said go from here to here. That looks like you're going across 2 bonds. So it looks like it's going to be twice the angle, but it's not. It's actually still 109.5 degrees. And let me show you why. Okay. Let me grab our tetrahedral here. Okay. Actually, close that. All right, take a look at this. Here's our AB4 right there. You got your central atom, 4 surrounding atoms. So, it's clear going there is 109.5. But really what they're asking you to do is now go from here. Let me put the OH in there. I'll put the O so you can see that.
So it's kind of three-dimensional. They're not going across one axis, they're going like across two axes. So it's
Yeah, well, let's see. Well, that's true. So really what they're saying is go from here to here. They're saying go from, you know, this hydrogen to this one. But keep in mind, any of these H's, they all, you know, they all have the same angle with respect to the OH. So it was a trick question. What they were kind of trying to get you to do is to go like to here and then to there, or from here and then to there. But that's not how it works. The angles are, what's the angle between the central atom and the surrounding atom up to the surrounding atom you're interested in? So that angle there is 109.5, a little more than a right angle. But so is this one. This is also 109.5. And so is this one. This one is also 109.5, right? So the Lewis structure, again, they're using the Lewis structure to confuse you, to make you think that you can use the Lewis structure to actually predict the angles. And Lewis structures do not give you angular relationships. All they do is give you arrangements of electrons around the central atom, right? And they do give you some information about bonding, right? A single versus a double or a triple, but they don't actually give you, that's a weakness of them, right? They don't give you the angular relationships. And so, you know, for that one, that would be 109.5. That would be, you know, any two of these surrounding groups are going to have the same angle with respect to each other, 109.5. Okay. So it'd be kind of like, you know, just to show you one that's a little simpler. Here it is. Here's our trigonal planar. So imagine I put, you know, a different group on here. So here's our trigonal planar, right? Only got 3 groups now. Suppose I said, hey, what's the angle from here to here? Okay, well, that angle would be 240 degrees, but that's not, you know, that's not what you would do. If I said, what's the angle between here and here? You wouldn't go around that way. You would just go around that way. It would be 120 degrees. So be careful with that one. If they're, you know, you got to make sure you have the arrangement of the atoms using the VSEPR theory to be able to predict the angles. Okay. Let me see what else we got in here. So those are simple organic ones. So that's, you know, kind of a common type of problem. You know, really these shapes are really useful for organic compounds. So that's why they're there. Okay, I'm up for this. Let's try this one. Okay, this one, you want to predict and name the shape of the molecules with a central atom. So answer the questions in the table below about the shape of this tetrachloroiodide anion, right? That's a mouthful. Tetrachloro, meaning there's 4 chlorines around the iodide. So there's an iodine there, right? You see the ICl4 minus, and it's negatively charged, so it's an anion. What word or 2-word phrase best describes the shape of the ICl4 minus anion? And then what is the bond? What is the angle between the iodine chlorine bonds? Okay. Well, you know, it's ICl4, so there is a possibility it's tetrahedral 109.5, right? But you have to be careful because that iodine, you know, it's in the 5th row. It might probably have lone pairs around it. And if it has lone pairs, that's going to kind of change the arrangement. So this thing might actually have like 1 lone pair around the central atom and 4 surrounding atoms, or it might have 2 lone pairs around the central atom and 4 surrounding atoms. And then that's going to have an arrangement based on that one. Okay. And then what are the angles there? So let's take a look at this one. Okay, so there you go. So again, you draw the Lewis structure just to figure out how many lone pairs there are. Okay, so you know you got 4 surrounding atoms. We know it's going to be negatively charged, so I'll put the brackets around there. So this is working on the Lewis structure. Okay, now we got a lot of electrons. Those halogens all have 7 valence electrons, right? They're in group 7A. So all 5 atoms have 7 valence electrons. So it's actually, you know, why 5? Because you got 1 there and you got 4 there. So that's 5 times 7. But then you got this negative, so you add 1 more. So 36. Now I've already drawn in a bond to the surrounding atoms. So we subtract 8. So that gives us what, 28? We get all the surrounding atoms up to 8. And you can tell we're going to have electrons left over, right? Because 6, 12, 18, 24, we got 4. So we have 2 lone pairs. So typically with Lewis structures, you draw them kind of like this. You put them on the sides like that. So, okay, expanded octet, right? We talked about that in chapter 8. Do a formal charge calculation, and what you would find is that the iodine has a formal charge of 0 in this arrangement, or is it -1? What is it? 7 minus, oh, it's -1. So it has a formal charge of -1. Okay. And there you go. All right. So now what's the arrangement? Well, oh, this one's a good one. You got 4. I like this one because you got the 4 surrounding atoms. But you got your 2 lone pairs. Right? So it's AB4E2. And that one we called square planar. Oops, gotta spell it right, right? Planar, planar, right? Square planar, 90 degrees was your angle right there. Okay, so the square planar, I think I showed that one to you, if I can find it here.
Wait, hang on. How did you arrive at 2 lone pairs again?
I just had to fill in all the electrons, right? So you knew you have 36 electrons. 8 of them are used for these bonds. Okay, so that's 8 right there. Then you get the lone pairs around the surrounding atoms to get the surrounding atoms up to 8, right? Octet rule for the surrounding atoms. So that was another 24. So that left us with 4. There's nowhere else for them to go other than to the central atom with lone pairs. So the iodine has 2 lone pairs. There's your 4. It has 8 with the bonds. And then each chlorine has 6, right? 3 lone pairs. So all that's it's all got to add up, right? If you start with 36 electrons, you got to end with 36 electrons. So there's nowhere else for them to go. And then let's see. So that's square planar. I thought I built a square planar here. It's weird. Seems to have disappeared. The square planar disappeared. I know I showed it to you. It was the one with 2 lone pairs. That's why. Oh, here we go. I'm sorry. I couldn't find it. Okay. So iodine in the center, 4 surrounding atoms, 2 lone pairs. So that's A, B4 or AX4, E2, 2 lone pairs on the central atom, right? So that's why those 2 charts that I went over, those are essential. Well, they're not essential, but they're very useful for doing these kinds of problems, because once you've got that chart, you know, usually it's easy to remember the linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Those 5 are pretty easy. But once you start getting up to, like, you know, 3 surrounding atoms and 2 lone pairs, or 4 surrounding atoms and 2 lone pairs, you know, then it's like kind of hard to memorize those ones. Okay. But, you know, in all, there's around, it's like 10 or 11 in all of these structures. We've got 10 or 11. Okay. All right. Let me show you now. We're going to talk about molecular polarity. And this is section 9.2. Okay, and it's essentially just an extension of what we've been talking about here. If you recall, when we talked back in chapter 8 about dipoles, remember we said that if you had two atoms bonded to each other, and it didn't really matter whether it was a single, double, or triple, but it actually does matter, but for the most part, we can ignore it. So you got two atoms, they're bonded together. And we said that this one had a higher electronegativity. Remember the electronegativity chart? Let's say this one was 3.5, or actually, let's make it simpler. Let's make this one 4.0. And we said that this one over here was, I don't know, 2.8. Okay. So this might be fluorine, for example, and this one might be iodine, for example. What we said was that if there's a difference in electronegativity, the atom that has the higher electronegativity will develop a small negative charge, and the less electronegative atom will develop a small positive charge. So we use the symbol delta to mean small. So if we say delta plus, we mean a small positive charge. And if we put delta negative, we mean a small negative charge. Electrical charges we're talking about, okay? So there's a significant difference between those two electronegativity values. It's a difference of about 1.2. So we would say that there are charges on that. And what we said was that we would then call this bond polar. Okay, or some people call it polar covalent, because it's still sharing electrons, but it's a polar bond. Okay. Now, the more technical term for this is dipole moment. We would say that the bond possesses a dipole moment. Okay, that's the technical term that we would use to describe that. And the idea of a dipole, pretty straightforward, is that if you have two objects that have a relationship with each other, meaning there's some distance away, and they have either opposite or similar charges, so they could be both positive, both negative, one positive, the other one negative, you develop a electric field, so it affects the space around it, and we call that a dipole. So the dipole is represented with a moment, and the moment is represented with a vector. We use a vector to represent that moment. And a vector has magnitude, which is essentially size, but it also has direction. Right? So vectors are very interesting quantities. They were essentially invented by Lewis, the guy that did the I'm saying not Lewis, Gibbs. They were essentially invented by Gibbs, the guy that worked in thermodynamics. And what they wanted to do was they wanted to represent something that had a direction, but also a size. Okay, so these dipoles, they are vectors. They have a size and they have a direction. So we use vectors to represent that. So, if you have the negative charge over here and you have the positive charge over here, we would point the vector, the arrow, in the same direction as pointing, along that line toward the negative. The head of the arrow goes in line with the negative, and the tail of the arrow goes in line with the positive. Okay. The length of the vector represents the magnitude. The magnitude is essentially the size. So let me give you a couple of numbers here just to kind of show you what I mean by that. Suppose I have a bond and delta plus is like 0.1 charge units. And delta minus is minus 0.1 charge units. Now, what do I mean by charge units? I mean this. An electron has 1 charge unit, or -1. Okay, a chloride ion, Cl minus, has a charge of -1. That's how many charge units it has. A sodium ion is +1. A calcium ion, which is +2, has a +2 charge units, right? So when I say 0.1 charge units, what I'm saying is it's a 1/10 of a unit charge. It's a 1/10 of the charge of a sodium ion. If I say it has -0.1, I mean it's a 1/10 of the charge of an electron. So those are pretty small charges, right? Not as nearly as big as the electron or the chloride ion or so forth and so on. So here's what you do. If you have a small charge, you just draw a short arrow, right? So notice the arrow is pointing in the direction of the negative, away from the positive. The tail is the tail of the arrow of the vector is in line with the positive charge. Now let me do it this way. Suppose we have, let me do it actually this way. I'll put the negative there and put the positive there. And delta plus is 0.3 units. And delta minus is minus 0.3 units. Well, now the negative's over here, so we're going to draw the vector that way, drawing in that direction. But it's also going to be 3 times as long as this one, right? Because this one's only 0.1, so it's going to be short. This one's 0.3, so it's going to be longer, right? So this would be like 0.1, 0.2, 0.3. So the vector again the vectors have 2 things you want to take into consideration. One is the direction. The other one is, the other factor is the magnitude, the size of this quantity. Okay. So if you have 2 atoms that are bonded together, so there's HF, and I do their electronegativity values plus, 2.1. That's the electronegativity value of hydrogen. This is the electronegativity value of fluorine. Compare that now to HC. Well, here the electronegativity again is 2.1, but this one's only 2.5. Now there is a difference, but it's not nearly as large as the HF, right? So here's how we would represent this. This is going to be a pretty long vector, and this one's going to be a lot shorter, right? Hopefully that makes sense. The smaller the electronegativity difference, the lower the magnitude, the lower the charges, the smaller the charges are on the atoms. So the vector will represent that by being shorter. The larger the electronegativity differences, so HF, for example, the greater the charges on those 2 atoms. Now, those charges are still not, they're not +1, -1, but they're getting close. It's maybe like 0.6 and -0.6. So that particular vector is going to be a lot longer. And again, the head of the arrow should be in line with the pointing in the same direction as the more electronegative atom. So the head of the arrow is negative, the tail of the arrow is positive. It wouldn't have to be that way necessarily. We could do the reverse of that, but that's just what we've decided to do. Okay. Now, the reason this is significant or important to us is that when we start talking about molecules very often have more than two atoms, and more than one of those bonds might be polar. So the question is, what happens when you have more than one bond and they're polar bonds or they're not polar bonds? What happens to the molecular polarity? Not the polarity of the individual bonds, but the sum total of those polarities. And here's what happens essentially. Molecules with multiple surrounding atoms have molecular polarities based on the sum of the individual bond polarities. Okay, you have to sum up the individual bond polarities, but here's the issue. Bond polarities are vectors. And vectors have a different set of arithmetic rules than simple addition. So if I add 3 cats plus 4 cats, I have 7 cats. But if I add 2 vectors that have a magnitude of 3 and 4, that answer might not be 7 because it depends on the direction of the vectors. So what I mean by that is, suppose I have a vector and this one has a magnitude of 7, and I have another vector and it has a magnitude of 7, but it's pointing in the opposite direction. The answer to adding those two together is not 14. You know, if we call this vector A and vector B, we would not claim that A plus B is equal to 14. It's not equal to 14. And the reason is the directions matter. Okay. Now, it turns out sometimes it's pretty simple. If they are pointing in the same direction, then they do add up very simply. You just add them together. Okay, that's cool. If they're pointing in opposite directions, so I'll call this case 1, and this is case 2. These are kind of the two simplest cases. If they're going in opposite directions, then one of them essentially has a sign of negative. And so you get 0. So 7 plus negative 7 is 0. So if they're in opposite directions, they cancel with each other. Here's case 3. Suppose one is going in this direction, and the second one's going in the opposite direction, but it's a different magnitude. Okay, well then in that case, A plus B equals 7 plus minus 3, which is 4. Okay, and so those are the 3 simple cases that you don't really need to worry about doing complicated calculations. If they're in between, if they're not in opposite directions or in the same directions, then the mathematics is a little bit more complicated, but we're not going to really deal with that too much in here. Okay, that's something you would do in a physics course. But we have 3 cases. One is they're opposite directions, same magnitude, then they become 0. Case 2, they're in the same direction. You just add them up. Case 3, they're in opposite directions, but the magnitudes are not the same. So then you just subtract them. Okay. So this one would actually be a vector. The resultant vector would be going in this direction, and it would have a magnitude of 4. This one would be really, really long. It would have magnitude of 14. And then this one would just be nothing, right? It would just be a point. It doesn't have any extension, any size. Okay. Now, since molecular bonds that are polar add as vectors, they're going to follow these rules of vectors. So here is a nice little example. I'm going to show you a molecule, which is carbon dioxide, and talk you through the whole thing. The goal here is to determine whether is the molecule polar or is it nonpolar. Okay. Now, our starting point would be probably to draw the Lewis structure. And so if you add up all the valence electrons, 4 for carbon, boy, 6 for oxygen, so that's 16, but we've used 4. So we put lone pairs on the surrounding atoms. Carbon only has 4 electrons, so I'm going to move a pair from each of the surrounding atoms. Okay, remember when you're doing different Lewis structures, you use the double arrow. Essentially, that's how you represent resonance. There's your CO2. So there's your Lewis structure, right? So that's just step 1. We did the Lewis structure. Okay. Step 2, figure out the molecular shape. So 1 is Lewis structure, 2 is the molecular shape. Okay, well, we have AB2, right? No lone pairs on the central atom. So that's linear. Okay, so now we have an idea of the shape, right? It's a straight line. So now step 3, look at electronegativity differences. Okay, so how do I do electronegativity difference? Well, this one's 3.5, this one's 3.5, this one's 2.5. Okay. All right, step 4, do the vector notation. Okay, so we're going to look at this bond first. So you do each bond separately. Carbon to oxygen. This one's more electronegative, this one's less electronegative. So we're going to draw a vector this way. Why is it pointing in that direction? Because oxygen is more electronegative than, Oxygen is more electronegative than carbon. So the arrow points toward the oxygen. But what about this bond over here? Same thing here. This one is going to point in that direction. Now, the electronegativity difference here is 1.0. And so is this one. So what do we have? We had case 1, case 2, case 3. Case 1 was where they're opposite directions, same magnitude. In that case, they cancel each other out and you get 0. So the vector A, vector B. So vector A plus B is equal to 0. If it's 0, that means there's no polarity. And we would call that a nonpolar molecule. So even though carbon dioxide has 2 relatively polar bonds, carbon-oxygen is a relatively polar bond, the 2 polarities, the 2 dipole moments add up to 0, because essentially you have one this way, the other one's the other way, and they're the same magnitude. That's case 1. It's nonpolar. So notice you can't really answer that question whether it's polar or nonpolar unless you have the shape of the molecule and you go back and you look at your electronegativity values. So let me show you an example. Here we go. An example of polar or nonpolar. Decide whether each molecule or polyatomic ion is polar or nonpolar. If the molecule or polyatomic ion is polar, write the chemical symbol of the atom closest to the negative charge. So which atom is negative? For example, if the molecule were HCl and you decided that the hydrogen atom was closest to the negative side of the molecule, you draw H on the last column. That's if you did that. Okay. So let's do F2 and then SiF4 and then H2O, and then we'll go from there. Okay. Each shape has its own specific answer as to whether it's polar or non-polar, just because of the geometric shapes. So F2 is simple. This one is nonpolar, and this is nonpolar. We actually covered that back in chapter 8, because it doesn't matter what the electronegativity of the atoms are. If you have the same atom bonded to each other, they have the same electronegativity. So the difference in electronegativity is 0. Fluorine happens to be the most electronegative element. 4.0 is its value. But 4.0 minus 4.0 is 0. So it's a nonpolar molecule. So that one would be nonpolar. But SiF4 is a little more complicated. So is H2O. So I'm going to look at these two and show you how to analyze these SiF4 and H2O. Let's do the SiF4 first. I'm going to do the Lewis structure first. So step 1, do your Lewis structure. In fact, I'm going to erase this. I may need a whole slide for each one of them. Okay, so there's your Lewis structure for the SiF4. The second step is you look up the you figure out what the shape is, right? So you have AB4, which is tetrahedral, which is 109.5. Okay, well, I'm going to draw it just to kind of show it what it looks like. Okay, there's your tetrahedron. Step 3, so 1 is Lewis, 2 is shape, 3 is electronegativity differences, right? So silicon is 1.8, or is it 2.1? I'm sorry, it's 2.1. And then fluorine is 4.0. That's a big difference, right? So that's polar, okay? So each bond is polar. But here's now what we do. We got to add the vectors. So remember, the fluorine's more electronegative. So here's what you're going to get. You're going to get an arrangement that looks like this. I'm going to add these vectors together. Now that is not obvious. The answer is, how do those 4 vectors add up together? It's not obvious. So I'm going to tell you right now that for the tetrahedral, the sum of all 4 vectors equals 0. They actually cancel each other out. It's a completely, I mean, it's a geometric problem you can solve. All you need is sine and cosine, but it's not something we're going to do in here. The tetrahedral arrangement, the vectors cancel completely. So that means it's nonpolar. If the vectors cancel, it's nonpolar. If they don't cancel, then it's polar. So that one's nonpolar. Okay. So let me show you the shape and whether it's polar or nonpolar. Because I don't have time, it would take us a couple hours to go through all of this. If it's linear, it's nonpolar. We did that with CO2. If it's trigonal planar, it's nonpolar. If it's tetrahedral, it's nonpolar. Okay, so we just did the tetra. I didn't even show you why that is for the tetrahedral, but they just add up to nothing. And let me just show you real quickly here. It's, you can sometimes you can sort of see it. Essentially what happens is you have one vector going straight up like this. Okay, one's coming out, but it's not coming out completely towards you, just sort of it's off a little bit. So up, these three though, all three of these are going down a little bit, but they're only going down a little bit. So a little bit down, a little bit down, a little bit down, a lot up. The three down cancel the one up. And then this is going up, so it's not going this way. These two are a little bit to this side. This one's a little bit more to that side, so they cancel in that direction too. So it just ends up being 0. So those three are nonpolar. They just work out to be nonpolar. The next one does too. Trigonal bipyramid, nonpolar. Octahedral, nonpolar. So all 5, remember these were AB2, AB3, AB4, AB5, AB6. They're all nonpolar. So if all the surrounding atoms are the same, and it's one of those shapes, it's nonpolar. All 5 of those shapes are nonpolar. Okay. So then you say, well, wait a minute, is anything polar? And of course, there's some things are polar. And what happens is you get to the next table. So remember, we had the bent, we had the trigonal pyramidal. These two are polar. Okay, those are the 2 polar substances. So an example of that, I want to show you why they are. It's not obvious. So here's the bent arrangement. The lone pairs are not shown here, but that's okay. This is bent. The reason this one is polar is because this vector here and this vector here don't cancel. If they were linear, they would. It's hard to get that up. So this right there, linear is nonpolar because they're opposite directions. But if they're not opposite directions, they don't cancel. In fact, if they're in this arrangement, they actually become additive. So let me show you the water. That's actually water. Again, you do the Lewis structure first. Then you do your shape. Okay, so it's bent, right? 104.5 degrees. Why is it bent? Because it's AB2E2. Easy enough, AB2E2. Okay, so now let me show you the vectors. This one is 3.5, this one's 2.1, and this one's 2.1. So you have one vector going like this toward the oxygen, right? It's going to be a relatively long vector. It's large magnitude because it's a big electronegativity difference. This one here, though, is also going to have, so let me call this bond A and bond B. It's going to be the same magnitude as the other one. It's just pointing in a different direction, but it's not an opposite direction. And that's the important point here. They're not opposites. Opposites would be pointing directly at each other. These both are going up. They're both going up. So that's additive in the y dimension, right? In the y axis. Now, in the x axis, they are going in opposite directions because this one's going this way and this one's going that way. So they do cancel in the x direction, but they're additive in the y. Okay, so those two do not cancel and it becomes polar. Okay, in fact, it becomes additive. So water is actually a very polar molecule because of this phenomenon. So the two that I just showed you, the bent These are going to be polar. And then your trigonal pyramid, pyramidal, AB3, E2, same thing. This one's going to be polar. Okay. So each arrangement has its own unique determination of whether it's polar or not, but the bent one is polar because of this geometry. Okay. So notice how involved this is now. You do a Lewis structure, you do the shape based on VSEPR theory, then you look up the electronegativity values to see if the bonds are polar. If the bonds are non-polar, if the electronegativity difference is too small, then the molecule will not be polar. So you have to look those values up first. Determine whether the bonds are polar or not. If the bonds are polar, then you have to connect them to the shapes. So those first 5, the ones where you don't have lone pairs, they were all nonpolar. But the ones that do have lone pairs, those ones are polar. Okay, so AB2, E2 bent, and AB3, E1. I'm sorry, I made a mistake here. This is E1. These ones are both going to be polar. Okay, there you go. And then that's pretty much all you need to do with that particular section, is just to be able to answer whether the substance is polar or not. And it looks like they usually give you one where it's just 2 atoms and the 2 atoms are the same element. So that's going to be nonpolar. And then you just have to do the shape to figure out the other ones. And they're not going to give you any complicated ones. They're not going to give you like a T shape or a seesaw. They're just going to give you one of those 5 shapes plus the bent and the trigonal pyramidal. Okay. And then you'll be set. Now, there is one more additional aspect of this to consider. And that is what happens if you have more than one type of surrounding atoms. So what if you have A, B, 3, C1, something like that, right? Okay, this is a different type of surrounding atom. Well, the first thing to say is that in terms of the shape, it doesn't matter. The shape is just an atom is an atom. A group is a group. It doesn't matter. But in terms of polarity, it matters. And here's why. Here's CH3Cl, okay? Carbon, you want to put at the center whenever you do these Lewis structures. So here's your CH3Cl. I'm going to complete the Lewis structure here just like we did before. The shape, you would treat it just like we did before, just like CH4. It's AB4, so you've got, this is in terms of the shape, so it would be tetrahedral. Okay, now I'm going to draw it. We're going to put the carbon in the center. We're going to do 3 hydrogens and 1 chlorine. Okay, tetrahedral. Now, electronegativity values 3.0, 2.5, 2.1, 2.1, 2.1. Keep in mind that depending on where you get these electronegativity values, they might be a little bit different. They might vary a bit. You might see 2.2 for hydrogen. You might see 3.1 for chlorine, but that's okay. It doesn't matter. So now here's what happens. This bond here is only slightly polar. It's a little bit, right? The difference is 0.4. So there's a tiny bit of polarity there, and it's going to point towards the carbon. Okay, so here's your carbon, here's your hydrogen. Same thing out here. It's going to point towards the carbon, right? Because it's the more electronegative element. But now here's what happens. This is interesting. The chlorine is the more electronegative element. So that vector goes that direction. So notice what happens. Essentially, this bond right here is going to kind of like, there's going to be some cancellation there. but this one's pointing downward and this one's pointing downward, and only one of them is pointing upward, right? This one's pointing down, 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 up. 3 of them are down, 1 is up. So they don't cancel. So if they don't cancel, that means they're going to add to something that's non-zero, right? They're going to add up to something. If they don't cancel completely, then you've got something, which means it's polar. So if you have a formula where you've got 2 surrounding atoms, very often one of them is more electronegative than the other. That's just typically the way these things work. And if that's the case, then in general, it's going to be polar, even if the shape suggests otherwise. The shape suggested that it would be nonpolar, but by having a surrounding atom that is different from the other ones, that will very often switch it to being polar. So if you see chlorines and hydrogens mixed together, they're typically polar. If you see fluorines mixed with hydrogens as surrounding atoms, it's generally polar. Okay, so that's sort of the last kind of nuance to those sort of problems. And that's the end of section 2. So we're going to switch up now to section 5 tomorrow. We're going to do hybridization. Okay. And so I'm going to talk about hybridization in small molecules. We'll cover that tomorrow. Tomorrow's Wednesday. And then I guess next Tuesday, that's when I will wrap up chapter 6 and do the molecular orbital theory. So I'll do section 9.6 next Tuesday. And then get into chapter 11. I do want, because chapter 11 is another extra credit exercise. So I'll start working on chapter 11, next week. I did want to spend a lot of time on the molecular geometry because it's important, but I wanted to also have a full day to talk about hybridization, which will be tomorrow, and a full day to talk about molecular orbital theory, which will, I'm not going to lecture on Thursday, but I'll do molecular orbital theory next Tuesday, and then get into chapter 11 as our final kind of extra credit assignment. Okay, so great. So we're moving along here. It may be that you're still working on chapter 8 and all that stuff. That's perfectly fine. So you can get to this when you get to it. But have a great day and have a great week.
Thank you so much. Bye.
Take care.